Start down. So this morning we're going to talk about a design technique called dynamic programming. And sort of with last lecture and this lecture, we're starting to really launch into the design phase of the course. So we spent the first part of the course working on the sort of analysis phase of learning a bunch of techniques, mostly with the example of sorting. And now we're sort of launching into the design phase. And the design phase culminates with our take-home quiz 2, okay, which is basically a design exam. So it's not the design exam doesn't test regurgitation of material. It instead tests how creatively can you put the ideas of the material together. And then for people who are really interested in design, we're going to have a programming contest that will start the day that the take-home comes back. Okay, which is a week-long contest where people can use their creativity to develop some a good program based on algorithmic and other techniques. I mean, programming is a lot more than just algorithms. Okay, as I think most of you know. So anyway, so today we're going to talk about dynamic programming. It's one of my most fun topics in this class. As I mentioned, this is a design technique. Much like divide and conquer. And the way that I'm going to present this technique is through an extended example. And that's the example of the so-called longest common subsequence problem. Okay, so in this problem you're given two sequences, finite sequences. X going from 1 to m, and y going from 1 to n. And what you have to do is find a longest subsequence common to both. And here, let me just mention that here I use the term A, not the, because generally it's possible that there's more than one longest sequence. Okay, so we talk about a longest common subsequence, not the longest common subsequence. However, what you'll discover is that everybody pretty much slips at one time or another and says the longest common subsequence. But what they really mean is a longest common subsequence. So when people say the longest common subsequence, it's again one of these abuses where we don't worry about it too much, okay? But we know that they mean a, okay? It's one of these things where, you know, the exact English is not necessarily what everybody goes by. Okay, so here's an example of this problem. So suppose X is the following sequence. And Y is the sequence So what we want to find is something that's a subsequence of x and also a subsequence of y. And we want the longest such subsequence. So can anybody tell me what a longest common subsequence here is? There's actually more than one here, I think.
BCAB.
BCAB. Let's see. BCAB. BCAB. Is that the longest? That's 4. Yeah, that's the longest. Okay. Any others that are the same length? So, who said something? What'd you say? BDAB. BDAB, sure. Any others? Yeah. BCBA, BCBA. Good. Okay. So there are a bunch. Yeah, the one I picked was BCBA. And we'll use the notation that that's the LCS of x and y. And once again, although this is a, functional notation, okay, it's not a function. Okay? So when we say it equals that, we mean it is a longest common sequence. We don't mean it's the longest common. So we can say BCAB is a longest common sequence. But there may be other things that are a longest common sequence as well. So I'll abuse the functional notation a little bit here, because it just makes the math and English a little bit more compact. But everywhere we want to be very careful that we don't assume that it is the longest common subsequence, because there may be more than one, okay, as we noticed in this example. So you can sort of, this one's B, C, B, A. Whoops. That's the wrong place. B, C, B, A, if I sort of pair up what the things are. And the whole idea is I can pair things up and these lines don't cross, right? Some way of putting them in where they don't cross. If these things crossed, then that wouldn't be a legal mapping. Okay, so let's take a look at some ways of solving this this problem. Generally, when people go into problems, one of the biggest mistakes that designers of code and algorithms do is that they start out trying to get the most efficient algorithm on their first attempt, rather than just sort of saying, okay, so, let me bound my problem. Okay, this is often the case on exams where somebody goes after like the really efficient, maybe that really efficient algorithm doesn't actually exist. Okay, and then you have nothing. It's always better to sort of say, okay, I at least know it's not worse than this, and then I can work on the next level, always protecting my so-called downside. Okay, so we'll start out here with a brute force algorithm, just sort of so we can see where we stand. Okay, and the brute force algorithm is pretty simple. We just check every subsequence of x to see if it's also a subsequence of y. Pretty straightforward. Let's go through all the subsequence of x. So we can analyze this. Okay, so how long does it take me to check a given subsequence to see if it's a subsequence of y? How long is a check going to take me? So I give you a subsequence. I say, I give you a sequence. I say, is it a subsequence of y? How long will that check take? Yeah.
Order n?
Order n, yeah. Okay, it's pretty similar. I just simply have to start out here and just sort of check off each letter as I encounter it in my subsequence, in my potential subsequence. Okay, it's just a scan. And each one I just check off. So it's order n. Okay. Even if m is much bigger than n, so even if the length is way longer than n, of course, then I could just check in its constant time by just if I knew the length. But in any case, even if I didn't know the length, I can still scan through. It won't take me more than order n, because once I exhaust all the elements of y, there's nothing more to check. Okay. And how many subsequences of x are there? Yeah.
2 to the m.
2 to the m. Right. So there are 2 to the m subsequences of x. And the way you can sort of see this is I can look at a bit vector of length m. So imagine I have a bit vector So for every bit vector, it defines a subsequence. Where it's 1, those are the elements I pull out of the sequence. And where it's 0, those are the elements I ignore. Right? So a bit vector serves of length m. If I look at every distinct bit vector, that gives me a bunch of different sequences. Now, of course, I may have some repeated sequences in here. Okay? But in the worst case, you know, all the characters are different. And so then I'll have essentially 2 to the m subsequences of x. Okay? So the worst case running time is order n times 2 to the m, which is exponential time. Which is a technical way of saying that it's slow. Okay, exponentials, you know, very slow algorithm. So I hope through this people essentially understand what the problem is at this point. Okay, is that any questions about what the problem is that we're going to solve here? Okay, because we're going to see a much faster way of solving this problem. Okay, but I want to make sure everybody's with me with what the problem is and why sort of, you know, the brute force algorithm is, you know, not a particularly good problem. Okay, so the way we're going to do this is we're going to go through first we're going to understand the problem a little bit more, prove a theorem, and then we're going to use our theorem to develop a better algorithm. We'll come up with some other algorithms along the way. So the first thing I want to do is a simplification of the problem. And that is, we're going to look at the length of the longest common subsequence rather than the longest common subsequence itself. Because the length actually is unique, okay, of a longest common subsequence. Okay? And focusing on length, that's just a number. And once we've figured out an algorithm to compute the length, then we can go back and extend the algorithm that we get for length to find a longest common subsequence itself. So then we'll extend the algorithm to find the longest common subsequence itself, or a longest common subsequence. Okay? So what's our strategy here? Looking at length. So our strategy, this is where if you're solving this problem as a design phase, you got to sort of play around, figure out what your strategy is. Okay? And the strategy we're going to come up with, and this takes some intelligence. This doesn't, there's no algorithmic formula for the design of algorithms, unfortunately. Okay, if you study the content of things like 6045 or 6840, you learn that in computability theory, there are things we can't compute. It's one reason it makes it interesting. And one of the things you can't compute is algorithms for things, okay, that are provably efficient. So what we're going to do here for this strategy is we're going to consider prefixes of x and y. In particular, let's define C of ij to be the length, which I denote with surrounding things in vertical bars like absolute value, of a longest common sequence of x, but only the part that goes up to I, and y, but only the first part which goes up to j. And I'm going to be worried about computing C of ij. Okay, why is this sufficient to compute C of ij to compute the length of a longest common sequence? How do I get the length of length of the longest common sequence of x and y once I have this? Yeah.
C of mn?
Yeah, C of mn. Okay. Is just the length of the longest common sequence of x and y. Okay, by definition, because once we have x from 1 to m, that's just x. Okay? So this is sort of the construction line that you would have in constructive geometry, okay, where the line doesn't exist, right? But you have to figure out where it is to make your argument. Same sort of idea here. So we're going to define these lengths of prefixes, where I can have a prefix of x and a prefix of y. And now we're going to be able to get a recurrence for the I've lost my good eraser. Is it down there? Yep, there it is. Ooh, I don't want to get under there. That's all. Especially because I wore a dark shirt today. I reached down there to get the good eraser. Anybody have a long arm who's wearing light clothes? Okay. We'll use the lousy eraser. This one takes more work than the other one. If you ever become a professor, there are 3 things that have to be good for you to be able to give a good lecture. You need good chalk, you need a good blackboard, and you need a good eraser. Okay, if any one of those is off, it's a pain. Okay, and people, of course, produce lots of junk boards, lots of junk erasers, and lots of junk chalk. So, such is life. It's not the worst problem in the world. Okay, so here's the theorem. I can compute C of ij based on smaller values of C of ij, and in particular, So this says that I can compute the value of the length of a longest common sequence of x from 1 to I and y from 1 to j based on a longest common sequence, the length of a longest common sequence, either from 1 to I minus 1 and 1 to j minus 1 for x and y, or I minus 1, j minus 1, or I j minus 1, or I minus 1 j. Okay, so I'm reducing, in some sense, the size of my problem with this recurrence because the sum of the indices of these are all less than the sum of the index of I plus j. Okay, so I'm reducing the problem. Okay, and so this is going to give us a scheme eventually for being able to solve the overall problem more efficiently. So here's a proof of this theorem. Okay, so we start with a case when x of I equals y of j. Okay, so that's this case here. So I want to prove that Cij, if x of I equals y of j, then this is the formula that applies. Okay, so let's take a look at that. Let me draw a picture. So here I have x. Let's see here. So we have 1, 2, and let's let that be I there, position I. And then down here we have y, which is going to, that's position j. And something like that. And what we're saying is that if we look at the prefix from 1 to I here and 1 to j here, we're saying that these two values here are equal. Okay, in this case. And now what I want to prove is that that the length of a longest common prefix of up to this, but not including whatever character this is that matches, and up to here, but not including that, plus 1, presumably for this match, okay, is in fact the length of a longest common sequence for both of these. Okay? Any question? What we're doing here? Okay, so how should we start? Induction. I don't think we need to do induction here, because we're sort of doing the induction. So the way I'm going to start is by just saying, well, what is a longest common sequence? What is the longest common subsequence of those two prefixes? Let's call that z. So let's let, it's always nice to give things names. Z going from 1 to k, say, be the longest common subsequence of x of 1 to I and y of 1 to j, where Cij is equal to k. So we'll just give it a name, okay? And now what we're going to do is start taking a look at the structure of Z. Okay? So there is some longest common subsequence. We're just going to call it Z. So the first thing I claim is that Z of k is equal to x of I, which is, of course, equal to y of j. Why is that? I claim the last element, if I have a longest common subsequence and these two match, the last element must be that matching element. Why is that? Yeah?
If it doesn't include that one, then you could add that one onto the longest common subsequence, and that would be longer.
Right. Okay? So if it didn't have this character at the end, okay, then whatever longest common subsequence you had would stop before there in both of these. And then I could just add this to the end and it would be longer. Well, then it wouldn't be longest. Okay? So okay, any questions about that? Okay, justification. I want to go through this slowly and carefully because this kind of argument we're going to see a bunch in the next few weeks. A whole lot of bunch. Okay, this kind of, it's talking about something as being optimal and then making arguments about its optimality. And usually the way you do it is by doing things like saying, oh, otherwise you could extend it. You know, it wouldn't be optimal if the property weren't the case. Okay. So if that's the end, then what property do I have of Z of 1 to k minus 1? What property does Z, just the prefix of Z that doesn't include this matching character at the end, what do I know about that? Yeah.
It's a common longest subsequence of f of I minus 1, 1 to I minus 1, y 1 to j.
So you're saying it's an LCS of 1 to I minus 1 and 1 to j minus 1. So that's true. I'm not sure we can conclude that. In fact, that's what we want to show. Okay, so we're not quite sure that it's the longest one at this point. But we do know that it's a common subsequence. We have to make an argument. Okay, so one step at a time. One of the hardest things in proofs is holding yourself back. If you sort of, oh, I see where this is going. I can see that's true. I want to jump ahead. So what we know is that this is a common subsequence of x of 1 up to I minus 1 and y of 1 up to j minus 1. We don't know it's a longest common subsequence yet, okay, because we haven't proved anything about, its length. And in fact, that's what we want to show. So I claim, okay, that in fact Z of 1 up to k minus 1 is a longest common subsequence of x of 1 to I minus 1 y of 1 up to j minus 1. That's sort of the crux of the, is going to be the crux of the proof, is actually showing that that's indeed a longest one. We know it's a common subsequence. What we don't know right now is that it's the longest one. Okay? And the way I'm going to prove this is by contradiction. So let's suppose we have a longer one. So suppose, say, W is a longer common subsequence of these two prefixes. Okay? Which is to say that the length of W is greater than k minus 1. Okay. So what can I do here? How can I show that W couldn't actually be longer? Yeah.
You can add the kth element that was equal to xi.
Right, you can just add the kth element onto the other one. So this is an argument that we're going to see a lot of. It's called a cut and paste argument. Okay, which is to say you glue things together. Okay, you sort of glue things together, a piece of this and a piece of that. Okay, so we're saying, so if I take a look at W concatenated, so that's one notation for concatenation, okay, with Z of K, okay, that is a common subsequence of X and Y, right? Because W is a common subsequence of x1 to I minus 1 and 1 up to j minus 1. Okay, and so therefore, if I just add k to the end, then that's going to be a common subsequence of the whole thing. Okay? Okay, but, okay, the length of W concatenated with Z of K is now greater than K. Okay, because the length of W is greater than K minus 1, and the length of this is just therefore greater than K, because I've added one character here. Okay? And so that's a contradiction. Which proves the claim. Because we said that W was the longest one. Okay? And if there were a longer one, well then Z wouldn't be the longest common subsequence of X and Y. Okay, everybody with me? Okay. Okay, so we can now complete the proof. Okay, so if that's the case, then it means that Z of I minus 1 j minus 1 is equal to what? Good morning, class. Wait. K minus 1, right. Why is that? Yeah.
Because that's what we just proved by deleting the last element.
Yeah, since C of 1 to k minus 1 is the longest common subsequence, it's got k minus 1 characters, and that's the definition of C. Okay? Cij is the length of a longest common subsequence. So therefore, for I minus 1 to j minus 1, the answer is k minus 1. We know that. Okay? Which implies that C of ij is equal to C of I minus 1, j minus 1, plus 1. Because this is just k minus 1. Okay? Plus 1. And that's what we wanted to prove. Okay? For the top line of the theorem there. Okay? And I'm not going to go through the other cases. They're in the book. So the other cases are similar. Okay? That is, you take a look at what happens when they aren't equal, and then you end up with either the longest common subsequence, if they're not equal, either being a longest common subsequence of the first string with the prefix of the second, or the second with a prefix of the first. Okay? And it's going to be the longer of those two. Okay? And that's a similar type of argument. Once again, cutting and pasting, contradictions about what's actually the longest, and so forth. Okay? Same kind of argument. Okay? Same kind of argument. Is that believable? Theorem believable? Even if I haven't proved the other case? Okay? Good. Okay, so this actually, when you do dynamic programming, one of the key things is to identify when is dynamic programming appropriate. And this type of theorem is the kind of thing that you look for. And those are what we call hallmarks. So we have two hallmarks for dynamic programming. This is the first one. Okay. And that is that there's a property, when you look at it, of what they call optimal substructure. Okay. And what that says is that an optimal solution to a problem, by which they mean problem instance, okay, contains within it optimal solutions to subproblems. Okay, so this is worth boxing, because this is one of the key hallmarks of when dynamic programming is appropriate to use. Okay, if you notice this property. So in this case, one looks at the longest common subsequence here, and you say, oh, goodness, look at that. You know, in this case, if they're equal, if the last character is equal, then in fact, the first k minus 1 characters of that subsequence, in fact, are a solution, an optimal solution to a subproblem. Okay? So you have a solution to a globally optimal problem, and if you look within it, you've got solutions to subproblems in it. That's not always the case, okay, for problems. But when it is, one of the things you want to think is, hey, maybe dynamic programming applies. And what you then look for is the second hallmark. Okay? So it's going to take us a minute to get to the second hallmark. So is there any question about what I mean by optimal substructure here? Okay, so the point is that if I look at a solution, an optimal solution to the problem, then within that I can find optimal solutions to subproblems. Okay? There's going to be other ways of picking optimal there are going to be other optimal solutions in there of other subproblems that I can set up. Okay. So so let me just restate that. Okay. If Z is a longest common subsequence of X and Y, in fact, actually one can show something stronger, which I'll write here, then any prefix of Z, okay, is an LCS of a prefix of X and a prefix of Y. So I take any prefix of Z, not just the one that's one off, and the reason is I can sort of just do this inductively. Okay? So I'm always going to end up with a longest common subsequence problem within the particular solution that I found. Okay. So let's write some code, some pseudocode anyway. So here's an algorithm, recursive algorithm, for a longest common subsequence. I'll give it two strings X and Y and the prefixes that I'm going to be looking at. And the code just follows this. It says if X of I equals Y of J, so there's a recursive algorithm for computing the length of a longest common subsequence. Okay. So two cases. Which of these cases is going to be the worst case? This case or this one in an execution of this? The second one. Why the second one?
Because you're running the recursion twice.
Because you're running the recursion twice, that's part of it. Each subproblem is bigger. Okay? The sum of the two arguments here, which is a good measure here because those are both going down to 0, okay, are each larger than this one. The worst case of this code is when X of I is not equal to Y of J. Okay, so let's do a recursion tree for this.
Do you want a +1 in the first case?
+1. How about that? I sure do. Otherwise, it would compute something else. Not very interesting. Good way to propagate zeros. It's called a zero the array. Okay, thank you. How come my TAs have to find this out, not my class? I guess the TAs have been up already for a few hours. I guess I'm not working them hard enough at night, huh? Okay, so let's do a recursion tree. Okay, and I'll just start it out when m is 3 and n is 4. Okay, so let me just write the arguments. So 3, 4 is going to spawn two subtrees, one of 2, 4, and the other of 3, 3. So basically subtracting 1 from this index. Okay, so this is I and j. So subtracting 1 here, subtracting 1 over here now. Okay, if I do the recursion. And then okay, so I expand again. And what do we notice? New hands, new hands. Yeah. Yeah, we got this 2, 3 repeated twice. In fact, if we kept expanding this, if we kept running this recursive algorithm, okay, we would end up with, you know, a lot of repeated, you know, a whole repeated subtree here, right? That would be a lot of wasted work. Okay, what's the height of this tree? Okay, if in terms of m and n. Yeah. M plus n. Okay. And so the height is m plus n. And so the naive implementation of this recurrence implies that the work that we're going to do is exponential in the length of, you know, in m and n. Okay, because it's just basically 2 to the power of mn is how much work we're doing. And moreover, we're doing all this repeated work. Okay, which is really bogus. Okay, I mean, computing fast is sometimes, you know, not computing when you don't have to compute. Okay. So this brings up the second hallmark of dynamic programming. Okay. And that's a property called, whoops, called overlapping subproblems. And it says that a recursive solution contains a small number of distinct subproblems, which are repeated many times. Okay, and once again, this is worth boxing. Okay, just like in grade school, right? The teacher would big box around things. Oh, yeah, make sure we write those things down. Okay, same thing here. Okay, make sure you write this one down, too. Okay, so we have two hallmarks. So we have overlapping subproblems. How many, for longest common subsequence, how many subproblems do we have? M times n. Yeah, it's just mn. Okay, why m times n? Why only mn? Why are there only mn? Everybody's learned not to be in the back right here. And I'm going to pick the lower left. Get people to move around where they sit. There's no place to hide except don't show up. But then you don't learn as quickly. So why only mn subproblems? What's a good argument to say that there are only order mn subproblems? Yeah?
You have n possible values for length x and n possible values for length y.
Right, you have m possible values for the length of x and n possible values for the length of y. So if I look at that whole set of possibilities for the Cij, I just need them to run from essentially 1 to n. So, and 1 to m and 1 to n. Okay? In fact, it's just the size. So how might I optimize this code? Yeah?
You could memorize it.
Could memorize it. So who remembers memorization from 6001? They teach memorization anymore? Yeah? Occasionally? Always? They did, but I forget what it is. Okay? Yeah, is basically you can memorize this, code. Let me toss that up there so we can still see that code. We'll erase this hallmark. Okay. So this is not memorization. This is an invented word, by the way, memoization. Okay? In fact, all the spell checkers bring it up. We even get people, when we use it in our textbook, get people writing in saying, oh, you misspelled memorization, all over the place. Okay? No, it's memoization. And the idea of memoization is that after computing a solution to a subproblem, we store it in a table. And then subsequent calls check the table to avoid you doing work. Okay? So I can either write it out again or I can just edit. Edit is always lousy for taking notes. We're going to edit anyway. Okay? So basically what I do is I wrap this whole thing from here down to, or let's say there down to there, in a test that says if C of I j equals nil, whoops, then we do all that stuff. Otherwise, there's nothing to be done. Okay, so we just stick that right in here. Okay. So if we have our table initialized to all nils. Didn't show the initialization. Okay? And then every time we have to compute something, well, if it's already computed, there's nothing to be done. We just return. But if it hasn't been computed, then we go ahead and compute it. Okay? So all this is just exactly the same as before. Okay? Oof. Any questions about what that algorithm does? Why it works? Okay, we just remember the stuff that we've computed. I see some quizzical looks. Did I make a mistake? Okay. So what's the running time? Yeah.
The time to compute a subproblem, and then the number of times that the subproblem is repeated, the time that it takes to check it each time.
Okay. So how much is that?
Order n plus n.
Order m plus n. Nope. Good guess. Good guess. Order m times n. That's right. Ooh. Why is that so? Okay. Notice that this is just constant time per entry. But goodness, sometimes you're doing all this computation, sometimes you're not. Why is this order mn? Yeah?
Because eventually you're going to fill in the whole table. And LCS gets called, and it actually does work once per entry in the table.
Yeah, but you're doing all these lookups too. LCS gets called more than once per table entry.
But it only does work once per table entry.
But what if I do a lot of calling?
You just keep checking it. It's already done, it's not really done.
Yeah, you still have to check. You have to add that into the cost of what the algorithm is. You can't just say the checking is free. It's not free. Yeah, but you still have to do the actual check. You still have done a call, a function call, and you've got the check if xi equals yj.
But see, the checking actually never gets done. Like, the LCS never gets called more than once for all the lower level subproblems. Because they get called once by the upper ones and then they worry about it.
No, I mean, it does, and then you have to check it. I mean,
this column on each ij, each pair of ij?
Yeah. Okay, that's one way of doing it. Yeah.
It's like in that example, like it'll call like for the 2, 3, but it won't call 1, 2, and 2, 3. Also, like for like.
Well, so to call for the 2, 3 here, right?
Yeah, like it'll
Okay.
only call it once.
But here, right here, it doesn't have to call this stuff. That's right. Okay, this one will just return. But I still have to call it, so I got 2, 3 appearing more than once. Yeah, actually, amortized analysis is one way to think about this. That's good. That's good. How can we use amortized analysis here? Set it to be the number of what? Right, either the nils or the filled, right? Okay, so the nils. Can set the potential energy to be the nils and start out the potential energy as being m times n. Okay? So that's one. You actually can work that out. I think that there's a little bit sort of a counting way. One of the ways of doing it is when you look at this code, don't break the code on the call boundary. Break it after the test. So in some sense, this guy pays, I want this guy here to pay for the call to these guys, right? And so this guy pays for, this guy up here is going to pay for these guys down here. I guess he doesn't pay for himself. So you don't pay for yourself, you just pay for the calls you make. Okay, so one way of viewing that is, see if I can be, is that we break the code, let's see, we break the code right here. Okay, so right there, I'm going to break the code and charge everything up to this point to my parent, including the procedure call. All this is going to be charged to the parent. And how much am I charging to the parent if I do that? Yeah, a constant amount. Okay, it's only the actual calculations now that are going to be charged to that particular entry. So I'm doing a kind of amortized analysis where I'm going to charge each cell for a certain amount of work. And the point is, lookups of a cell are not going to be charged to the to that cell. They're going to be charged to the cell that is doing the lookup. And how many cells does any cell have to look up? How many other cells? We can just look at the code here. Yeah. At most two. Either 2 here or 1 there. Okay, but at most 2. Each of them is only going to do at most 2 lookups. If I charge the lookups, so I charge the lookup of I minus 1j here to the ij computation. Okay? And so each cell, ij, is only going to have to look up at most 2 other cells. And then if any calculation goes on, those get charged to the cell in which is we're filling in the calculation. Okay? And then the amount of work there is once again constant, because everything is either just a bunch of lookups or else the constant work. So there's basically constant work per cell that has to go on. Okay? And they're m times n cells. Okay? Is that clear? And yes, you can make this an amortized argument. with potential functions if you wish. Okay, this is more like an accounting argument, where we account by putting dollars throughout all the nil cells or whatever. Okay? And I have enough dollars on a cell to look up things in the, to pay for the constant work to look something up. But if that cell needs to calculate, well, it's got dollars that it can do to do its lookups, and whatever the other constant amount of calculation, like the plus and the comparisons and so forth. Okay? So is that clear? So it's order mn time, constant amount of work per entry. Okay, so that's we're going to see a lot more algorithms where you're playing this kind of accounting game in order to do the analysis. The analysis is pretty straightforward and actually quite simple when you understand it. But initially, to sort of get your head around, oh, what's going on and where am I charging things, a little bit thing. The other thing we want to look at is space. How much space does this algorithm take? Wave hands. New people, new people. Somebody who hasn't answered anything today. This is an easy one. Yeah.
Theta mn.
Theta mn, good. Okay, because there's basically the table and everything else is just small amount of bookkeeping. Okay. Good. Okay, so that's the memoization algorithm. That's a pretty good algorithm. Okay. Now we get to, and in fact it's the inspiration for the next algorithm, which is what we've been after the whole lecture, the dynamic programming algorithm. Now, so let me just mention here that programming in this context is the original term of programming was any tabular method. And computer programming came up because originally, to program a computer, you filled out a chart that showed what each instruction was, in fact, what the bits were in each instruction, and instruction by instruction. So it was a tabular method. We just call it programming these days, but it used to be called computer programming. Dynamic programming is another tabular method. There's another type of programming that people may have heard of. What's another type of programming? Linear programming, where there's a tableau that represents a matrix, and you manipulate the matrix. Okay, so there's the term programming is a more general one. Okay, so this one, dynamic, I don't know how they got the name dynamic. I mean, it's like... The basic idea behind dynamic programming is to compute the table bottom up. So here was a recursive top-down one. But in fact, rather than starting at the top and doing all this recursion and everything, let me just start at the bottom and compute it up. So let me give you an example of that. Let's see, I think I can do it here. So there's one string with a 0 there. Whoops. Another string there. And I'll initialize things across here as being all zeros, because basically the boundary case is that if I have a longest common substring of any string with the empty string, length of a longest common subsequence is 0. And so then what I'll do is I'll just go in and I'll use my formula to figure out what this entry is, which I can do because it relies on either these two values or that value if these two things are equal. So what's this entry going to be here? What you're asking here is what's the length of a longest common subsequence of B and A? 0. And the place it comes from is in the formula here, which we've got in code here, but which I probably erased a while ago, is it's just the maximum of the position which is above and the position which is next to it because A is not equal to B. Here A is equal to B. Excuse me, here B is equal to B, sorry. Okay, so what's the value here? 1. And so I can sort of draw a little line here indicating that this value came from there, okay, because these were equal, so it's 1 plus the value on the diagonal. That's what the I minus 1 j minus 1 says. That says it's the diagonal position. Okay, what's this value here? 1. And I got to put in a diagonal here because B equals B. Okay. One with a diagonal. Okay, so compute the whole first row. Now the second row. 0. 1, because it's the max of these two. Okay? Two with an A, because those are equal. 2, 2. Okay? And here, 0, 1, 2. Okay, let's go faster. Okay. Next line. 1, 2. 1. Okay, and that's the answer that I want, right? Longest common subsequence is 4. Compute it bottom up. I also could have computed it this way. I could have computed it this way. A bunch of ways to compute this table. But basically, it's bottom up. Okay, you can see this is a really fast algorithm compared to the recursive ones. Okay? But it's actually no faster than memoization. It's just a more orderly way of doing it. In practice, sometimes this is faster, sometimes this is faster. Okay? This can be faster in cases where you don't actually have to explore the whole table. Then there'll be some entries you don't have to compute at all. Okay, for some problems. Okay? This is generally faster, however, for a couple of reasons. One is because you can get a very regular movement of data. And computers like regular movement. If you have regular movement, the caching and the paging and so forth all works much, much better than sort of more random access into the table. Okay, so there are a couple things here. So the time for this is what? This one's really easy to analyze, right? Yeah, theta mn. Okay, really easy. There's just that many entries you're filling up, and you're doing constant work for each one. Okay, and what's the space? Theta mn also. Okay. How can I get the longest common subsequence out of this? Suppose I now want an actual sequence.
Just follow your little slashes.
Yeah, follow those little dashes. How do I do that? I start out here. I trace backwards. Okay, so we'll reconstruct. Okay, and here I don't have a diagonal, so I can go either way. In fact, I have a non-deterministic choice here. I can choose either one. Let's say we go this way. Okay, then I have a line here, so I basically go this way, and that means that B is going to be one of my numbers. Then I can go diagonally again. So now I get A. Okay. Now I can go either way I want. Let's say we go up again. Okay. And then I can go this way. So now I get another B. Oops. D. Where am I here? Sorry, D. I'm sorry. Yep. D. Good move. Good. And then for the next one, I get B. Okay, and then I march over. But I could go a different way. I could go this way here. And I would get a different longest common subsequence. Okay, so every time I take a diagonal one, you can go back. Okay. Now, how much space do I actually need here? I said it was order mn the way I showed it. Can we do better than order mn? Yeah.
Two rows in memory.
Yeah, you could keep just 2 rows in memory. You don't actually need, as we did this, all I needed was 1 row and the next. In fact, you can actually do even better than 2 rows. You need like 2 more than 1 row. Yeah, something like that. Yeah. Okay, you can get 1 row plus a little bit. In fact, generally what you'd do is you'd sort of keep a row like this and a row like this. Maybe it is 1 more. Is it 1 more?
Oh, you need 1 more than that from the previous. Because the last.
Yeah, because then you compute this. Well, when you compute this, you could throw away that. So it depends, yeah. So it's either 1 more or 2 more. Okay, and so forth. So a good exercise, actually. So actually, also, I'm doing this the wrong way because, in fact, I could do it. So this space actually can go to theta of the min of m and n. Because why not just do it in the direction of the shorter dimension? Save even more space. One thing that's actually turns out to be true in most computers is if you can make it use less space, it generally goes faster. Because you do much better to reuse existing space because then the caches in your computer work better. Okay, and so that is one reason, another reason why this bottom-up programming, not only regular accesses, which is good for caching, but also it is you can end up using only order min of mn space for this. Question?
If you only keep 2 rows, how do you trace backwards at the end?
That's the exercise. Okay, use small space plus reconstruct the LCS. Okay, that's a homework exercise. Okay, so very, very slick. So you're going to do, as part of your assignment this week, there's a programming assignment. It's the only programming assignment I give. You can do it in any language you want. And that is to solve actually quite an interesting problem, that of doing text justification using dynamic programming. And this is the algorithm that's actually used in LaTeX, which is a very popular typesetting program. Okay? So you'll get a chance to use a bunch of these ideas.